So let's do some more homework problems just to kind of keep getting some more practice. So in this next one, we're considering a point on the edge of a circle with a radius of 36 centimeters, and it has an angular velocity of pi over 24 radians per second. And we're asked to do the following. So just picture-wise, right, we know that our radius is 36. We're a point along the edge, and we know that we're rotating at pi over 24. So they gave us our omega. So there's omega right there, and there is our r right there. So let's see what we need, right? So it says find the central angle generated in 3 seconds, right? So what they're wanting us to do, that central angle is theta. So what formula do I use? Well, of the three that we have, and I should have reviewed that, right? So we know that linear speed can be given by the distance over time. Angular speed is my angle over a time, and my linear speed is the radius times omega. All right, and then the wild card is revolutions and 2 pi times revs. But in this case, I think it's pretty clear we need this guy right there. All right, and so omega is theta over t, which tells us that my central angle is omega times t, and I have everything I need. My central angle is the omega that's given, pi over 24, times the time that was given, which is 3, and you can write that as 3 over 1. So doing a quick cancellation, it looks like pi over 8. So our theta, our central angle in this situation, is pi over 8, and technically that would be in rads. Okay, so that's the answer for A. For B, they want us to find the distance traveled by the point along the edge of the circle. Well, if we're talking about how far we've traveled along the edge, we are basically talking about arc length. So this, we actually need our arc length formula, right? So the arc length is S equals R theta. So we're actually back to 3.2. We have everything we need. We know the radius, right? That was given. It's 36. And then in problem A, we found the central angle that's been swept in 3 seconds is pi over 8. And so we basically get 36 pi over 8. I think if we divide both sides of both of these by 4, we get 9 pi over 2. And this would be in centimeters per second, right? Centimeters because that's what the radius is measured in, and seconds because that's how fast things are moving. So centimeters per second. All right, or actually no, we're not talking a rate, we're talking a distance. So we basically just traveled 9 pi over 2 centimeters. Sorry, I'm getting into the next one. All right, so there you have it. So we actually had to break out an old formula from section 3.2. In the next example, they're asking us to find the linear speed of this point, all right, on the edge of the circle. So what do we know about linear speed? Well, v is equal to s over t, or v is equal to r times omega. And to be honest, I think we can use either one here to answer it, all right, because we have all the information that's given. So let's use this one first, since that's what we have been using. If we use that guy, we get that v is the radius, which is 36, times omega, which was given as pi over 24, right? And so our v is 36 pi over 24. I believe 12 goes into each one of those, so we get 3 pi over 2, and this would be centimeters per second because my length is measured in centimeters, right? And my time is measured in seconds. However, if we use this guy, right, we know the arc length, so we would have 9 pi over 2, and we know that the distance, the time that it took to go that, right, is 3 seconds. So this is basically 9 pi over 2 times 1 over 3, right, because that's 3 over 1. And so doing a quick division, right, we get 3 pi over 2, so we get the same answer. So that was a kind of unique situation. We have two ways to calculate my velocity. I can use the angular velocity route, or I could have used the s over t route, because in part B we actually found the arc length traveled. All right, so kind of an interesting problem there. All right, two ways to kind of tackle it because of the information that was given, but it also hopefully helps us trust, the formulas, that they do what they say they do. Alrighty, so how about the next example down here, number 5? We got a chain. It runs a bicycle sprocket that is of radius 8 inches at 50 revolutions per minute. All right, so do the following. So again, in terms of on a bicycle, there's actually 2 sprockets. So which one they're talking about, I don't know. But let's assume this one. So we have an 8-inch sprocket attached to a chain. Obviously, it's doing some rotating as you apply some force to it. So what's the angular speed? Well, omega is theta over t, all right? Or in this case, right, because we don't really have any time element in here just yet. Actually, we do, 50 minutes per minute. But what we can do, right, our omega, well, one full rotation is 2 pi, and we're told we do 50 revolutions per minute. All right, and so basically it looks like 100 pi rads per second, all right, because 2 pi rad for every revolution. So there's your angular speed. So we were able to find that since we're given revolutions, well, each revolution is 2 pi rad. I went through 50 of them, so we're going 100 pi rad per second. So what about the linear speed? Well, we're definitely using that formula because I have my radius and I just found my omega. So V is my 8 inches of radius times my 100 pi radians per second. So V is 800 pi. This would be inches per second. All right, and that is pretty fast. Okay, so I'll let you guys, again, that is in inches. We can convert it to feet and miles and all that other kind of stuff using some other math. But there's that round, using the formulas, using some past formulas, putting some ideas together. Hopefully it's helpful. And I think we got one more round of things to do. We'll try to even get more application based. But I'll do those in videos coming soon.